Hi everyone, in this video we're going to be talking about substitution. So our first example is actually one straight from the textbook, just that we can kind of talk through it together. So this is example 613 in your book. We have the integral of 7 over negative 3x plus 1. So what's important to notice here is it's kind of a weird arrangement, but if we shuffle that 7 in particular out front, we would have 1 over negative 3x plus 1 dx. And what we have is an integral where if this linear function, if this negative 3x plus 1 was just an x, we'd have 1 over x, and we'd say, oh, well, I can integrate that to the natural log of the absolute value of x, and we'd be good to go. So what we have here is a linear function where x kind of should be, or we would like it to be. That's an indicator that a substitution is going to be successful here. So in this case, we're going to choose u equals negative 3x plus 1. That's my linear function. So this is a choice right here. I'm going to choose u to be negative 3x plus 1. This is the step where you're somewhat taking a leap of faith. Sometimes whatever you pick here doesn't end up kind of working in the end, but you at least kind of have to try something. The next step here is to compute du. So that's always going to be my next step. So this I pick, and then from here I'm computing. I'm not actually like coming up with anything on my own. So my left-hand side is always du, right? Sort of the derivative of u. And then here it'll just be the derivative of this function, and then I'll throw a dx at the end. So the derivative of negative 3x plus 1 is just negative 3, so I'll say negative 3 dx. Now, there's usually, almost always, one extra step here, which is just to get the constant out of here. Because usually that negative 3, like we have a 7 running around, not a negative 3. So usually that constant is not exactly what you want. So I'm just going to divide both sides by negative 3. So I have, I guess, 1 over negative 3 du equals dx. That's just me computing. You don't really want to do that a whole lot with things other than constants. Usually it's just divided by a constant here. If there's other stuff, you would leave it. Okay, so now that we've decided on that substitution, we're going to actually plug stuff in here. So our goal is to write the integral entirely in terms of u and not have any x's left over. So I have the integral and I have the 7. 1 over this stuff is of course 1 over u. And then dx, I now have this perfect swap for negative 1/3 du. So I'm going to take one extra step here before I actually integrate and just combine the 7 and the negative 1/3, because those are just constants. So I'll combine them just into one number, and that'll carry down into my final answer. Right, so now we can actually do the integration step. Negative 7/3 comes right down into the answer. The antiderivative of 1 over u is the natural log of the absolute value of u. Don't forget those absolute values, they're always important. And then of course that plus c, that's always there. That's just kind of a constant and a constant. So the step we did here was actually find the antiderivative, or the indefinite integral. So my integral symbol and du are now gone because I've actually integrated, which means that now I'm free to go back into x. So once I integrate, which is what I've done here, my very last step is to switch back into x. So this u right here shouldn't be in our answer. So we're going to go back to the original choice of what u meant in terms of x, and just plug negative 3x plus 1 in that spot. So we have negative 7/3 times the natural log of the absolute value of negative 3x plus 1, and then that plus c sticks in your answer. So checking your answer is not required here, but it is kind of convenient sometimes, especially at the beginning when we're learning a technique. If you want to check that this answer is correct, just take the derivative of this function off to the side. You'd use the chain rule, right, where your inside function is this. And it should simplify out to be exactly the integrand that we started with. Okay, so that's my final answer here, and we'll do one more example in this video. So same method, same substitution method here, but now we're integrating something a little bit busier. So our substitution here is not going to be a linear function. So what we have is, of course, 6x e to the x squared plus 1 as my integrand. So my choice is going to be u equals x squared plus 1. This may not be your first choice. You may go a little bit bigger or a little bit smaller, but this is the one that's gonna get us to a final answer. So I've chosen this because it is in my integrand, right? X squared plus 1 is right here. And if that were just e to the u, I'd be good to go. And I can see this extra x, the 6 is whatever, but this extra x here, I'm going to have to deal with it. And I know that the derivative of x squared is 2x. So I have this function's derivative within a constant multiple, right? You're going to have kind of the wrong number out front, but it is at least that derivative within a multiple. So I'm going to go with x squared plus 1. All right, so that's my choice. My next step is to compute the du. So again, my left-hand side is du. My derivative on the right is just 2x, so I'll say 2x dx. And then I'm going to take that same extra little step as in the first example and just get this 2 onto the other side with the du. Because x dx I'll be able to swap out, but that 2 isn't right. So I'm just going to divide both sides by 2 from here to here. And then I'll have an easier time making the substitution in the next step. Alright, so now is the step where I want to switch from x's into u's. There should be no x's left over when I'm done in this step. Alright, so I have 6. The x dx I'm going to wait on and just say e to the this stuff is now e to the u. And then notice x dx is what's left over. And we have exactly x dx equals 1/2 du here. So I'll say, okay, that's times 1/2 du. And once again, there's a little bit of cleanup here, right? Like the 6 and the 1/2 we can turn into a 3. Oops, forgot my integral. So the integral of 3 e to the u du. And now this is something that I can integrate. So I want to pause here before I actually integrate it and point out. If you had kind of taken a guess here, right, because it's not always super obvious, if you had guessed kind of the wrong thing or something that wasn't going to work, everything would be fine until here. You would either get an integral where you couldn't get rid of all the x's, right, so you'd still have some x's and some u's, which is a bad sign, or you would get all into u's, but then it would still be something that you don't know how to integrate. That's another sign that you need to rethink what you chose for your substitution here. So if you make this substitution with the u and the du, it becomes, something entirely of u's and it's something you can integrate, then you're good to go. And that's what we have here. So my antiderivative is 3e to the u plus c, right? Because e to the u is its own derivative. And now that I've actually integrated, I'm just going to plug the x's back in. So instead of u in this spot, I'm going to write x squared plus 1. So in this final step here, you should never have to do any extra heavy lifting aside from just coming back to your original substitution. All this other stuff underneath it doesn't matter. It's just that original stuff goes back in for you here. And again, if you want to double check this final answer, if you take the derivative of this thing using the chain rule, you should end up with exactly 6x e to the x squared plus 1.